As you saw, the Java Executor's framework has a bunch of pieces. We're going to start by talking about the simplest of those pieces, which is the Java Executor Interface. And as we'll see, it's a ridiculously simple capability, mainly used just to kind of start things up, and we'll see how it gets used. So the Executor Interface provides a single method that's used to submit new tasks for execution. And the reason why it's there is to decouple the mechanisms of how you implement the tasks from how you actually get the tasks submitted. So it's a decoupled separation of concerns argument or approach where you can have different implementations that use the same common interface. Each task that is submitted to the executor implements Runnable, either directly or through a Lambda expression. So you hopefully have seen the Runnable method before. In fact, kind of along the lines of Sri's question, Runnable is what you give to a thread also if you're going to implement a thread. This represents a command to execute. So the instance of Runnable is a command that will be executed. And this is basically the command pattern, or at least the Runnable part is the command pattern. And this is a so-called gang of four pattern, which basically defines an object that's used to encapsulate all the information needed to perform an action or trigger an event that's performed later in time. So basically, you have this command with an execute method in the pattern, and here we have a Runnable with a run method. So basically the same idea. So you can make these things, you can kind of pass them around. Executor and Runnable, as you can probably ferret out from the fact that it has a single method called run that returns nothing, is used for so-called one-way task semantics. So that means it does not return a result. So you get it to run something, and there's no result that comes back. The reason I distinguish that or make a big deal about it is when we talk about callables later, when we discuss the executor service, and for your programming assignment that's coming up, you'll see that you get two-way semantics there, so you can get a result back. When you execute something with an executor, it might run in the background thread, like one of these guys, or it might run in the main thread, kind of like this guy. And where it runs depends on the implementation of the executor interface that is used to implement the executor interface. And we'll talk more about that in a few minutes. But you don't know, by virtue of the fact that something is using the executor, you don't know just because of the virtue of its interface whether it's running in the background or not. Typically it is, but it doesn't have to. This mechanism also, when you implement it and use it in practice, also is used to implement the so-called command processor pattern. And this is a pattern that goes above and beyond the command pattern to package up some application functionality in an object and allows it to be usable in another context. And that other context is typically in another thread of control that will run it in the background at some later point in time. So it basically ends up executing a request which gets handed off to the command processor, which usually enqueues it and then has it run in another thread of control in the background. That's the command processor pattern. You can read about that pattern here. Very, 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 very common pattern in concurrent programming. So as we'll see later, the executor framework uses it. Lots of the Android concurrency frameworks, like the Hammer framework, uses the command processor pattern, and so on and so forth. So that's just a quick overview of the Java Executor. As you'll see, there's not much to it, so we don't have to spend too much time on the executor because it's very simple. Now that you've learned the ridiculously parsimonious and simple-minded executor interface, let's see how we could actually apply it in practice. And we're going to use it to implement a prime checker app. We'll look at this from a number of different points of view as we go through these examples. This is basically going to generate a bunch of random primes, or random numbers, sorry, and then check to see if they're prime numbers. So let's talk about this app. This is a good example of an embarrassingly parallel app because it's going to try to check the primality of a whole bunch of numbers, which it randomly generates. And of course, each of these things can run concurrently. So as long as you've got cores to spare, you can run the computations all at the same time. And you can download the app here and run it. It's very simple, but it's fun. It's a cool example. This particular implementation, the simple-minded one we're looking at here, uses a fixed thread pool. And this particular thread pool is going to be given a parameter, which is the number of cores available on whatever computing device you happen to be running the app on. So if you run this on a single core machine, the value of this will be 1. If you run it on a dual core machine, the value of this will be 2. A quad core machine, the value of this will be 4, right? So it's basically it's calling a method in the Java class library called getRuntimeAvailableProcessors, which is actually sort of a goofy name because nowadays it means processor cores. But it's going to come back with a number that's the number of things it can run in parallel. Why do we use a count of the number of cores for checking the primality? What's the reason why we choose the number of cores for this? Can we think of why we do that? Let's assume we're not doing anything else on the computing device while we're doing this. Why don't we do number of cores times 2? Or why don't we do number of cores divided by 2? Bruce? That's how many threads we can run in parallel, but what is it about checking for prime numbers that means that if we had, double the number of threads, it wouldn't be a win? What's a prime number calculation? What class of calculation is a prime number calculation? Here's the two classes. I/O bound, compute bound. Compute bound, right. So if something's compute bound, what does that mean? Let me re-ask the question a different way. What does it mean to be I/O bound? Joe? Right, so if it was I/O bound, then when something's I/O bound, when a thread goes to sleep waiting for the I/O to show up, then you would like that sleeping thread to be parked off to the side, and then that core now becomes free until the I/O is completed, and you'd like to be able to have another thread that you can say, this guy's asleep, why don't you run and do some work and use this core in an efficient way? So for I/O bound tasks, you typically want to have a number of threads that are greater than the number of cores. In fact, you'd like to have the number of threads be roughly comparable to the number of things that are blocking at any given time. But a compute-bound task, like checking for primality, checking for prime number, whether something's a prime number and finding its prime factor, that doesn't benefit, it's not going to block. So there's no need to have more threads than there are cores, because those other threads will never get called, because all the other threads will keep running until they're done computing the prime number. So that's why we have the same number. Here's the prime number calculation. This is a brute force way of doing this, so it's intentionally meant to just burn CPU. There are much, much more efficient ways of computing prime numbers than the one that's shown here. But we're just trying to do this to chew up time. And this is inefficient for a whole variety of reasons we won't talk about. The way it works is it either returns 0 if the number is a prime, or it returns the smallest factor if it's not prime. The main activity for this program works as follows. It creates a new random number, and the random number has a method called longs, and longs is a generator, and so it actually generates a stream, a Java 8 stream, of this many random numbers, count of them, between 0 and max value. So it's going to generate random numbers between 0 and the max integer. And we're going to then, for each of them, for each of the random numbers that are generated, we're going to go ahead and say Executor. Remember, we set Executor over here to be the fixed thread pool. We're going to say Executor execute, and we're going to make a new prime runnable passing in this and the random number that we want to check to see if it's prime or not. So the way to think about this is, let's say, for sake of argument, we want to check we want to do prime number calculations for 25 prime numbers or 100 prime numbers or whatnot, randomly generated. There will be a new runnable for every one of those numbers, but they're only going to be m threads, where m is the number of cores. So you can see here we're bounding the number of threads we're using to a fixed amount, even though we may have lots of computations. So what does that imply? It implies all the other computations to be done, they get stuck into a queue, and then they get run in the pool of threads when there's a thread that's available, when it gets done doing whatever else was in the queue it had plucked off and worked on before. That's basically how this is going to work. So let's kind of talk about this. Is this good, bad, or what? So the main benefit of using the executor interface, rather than just spawning threads, right? First of all, let's go back over here for a second. We could have done this by spawning a new thread for every random number. But then we'd end up with a heck of a lot of threads, right? We'd have a thread for every number, which would be excessive, especially if we had a large number of random numbers to compute. Moreover, we would have hard-coded ourselves to one implementation, one type of thread pool. By using the executor interface, we can vary the implementation of the pool. We could have a fixed size pool, we could have a variable size pool, we could have a work stealing pool, all kinds of different pools, and all that has to change is the way we make ourselves the executor object, but this code here can look exactly the same. So we're separating out the implementation from the way it's used. So just a classic separation of concerns style argument. However, there are some limitations, and the limitations are here due to limitations or restrictions on the Java Executor Interface. It's very simple-minded. So it only has one-way semantics. So we're going to create a thread, or sorry, we're going to, we have no way of being able to cancel anything that's running. We have no way of getting the results back. That makes it very complicated, especially if you start rotating your phone. Weird things happen. We'll talk about that later in the class. So this becomes complicated, one-way semantics. We also tightly couple the prime checker algorithm with the prime runnable class. So these things are tightly coupled, kind of like a big ball of mud. And so one of the problems with this implementation approach is that if we come up with a better algorithm for checking for something's primeness, we're going to have to do some major surgery to our code. Because right now it's hard-coded to work only with this particular kind of implementation. So that's not good. The lack of lifecycle operations make it complicated for various reasons. We can't cancel or interrupt running tasks. If a task is running and we need to stop it for some reason because we're going to rotate the phone or whatnot, we can't easily do that. And this just makes things more complicated than they need to be. So the long and the short of it is that the Java Executor Interface is too simple for its own good. So we'd like to do something that's more powerful. And that, of course, will motivate the next topic. But we'll stop there for this second.